The second example in linear programming is a lot like the first one, with constraints on assembly time and packaging time. And I wrote it up really nicely, and it's in the files in Canvas. So if you want to look over that one, do so. And if you have questions on it, let me know. I'm going to make a video now for the third example, because it's quite a bit different than the first two. So this is about a mining company. The company owns 2 mines, and the mines produce ore that is graded into 2 classes, either regular grade or low grade. The company has to produce at least 420 tons of regular grade and 540 tons of low grade ore per week, probably because of contracts they have. The first mine produces 6 tons of regular grade ore and 18 tons of low grade ore per hour. And the second mine gives us the production for as well. It also gives us the operating cost of the first mine, which is $19,000 per hour, and the operating cost of the second mine, which is $13,300 per hour. The first mine can be operated no more than 40 hours a week, and the second mine can be operated no more than 38 hours per week. Our question is, how many hours per week should each mine be operated in order to minimize the cost? So the thing that we're trying to minimize here is the cost. And in this example, because it's called the first mine and the second mine, that doesn't work very well for my variables. So I'm going to name my variables X and Y. I'm going to let X represent the hours that the first mine is operated, or operating, I guess. And I'm going to let Y be the hours for the second mine per week. Okay, so if we want to write a cost function, and we know the operating costs are given to us right here, the operating cost of the first mine is $19,000 per hour. So $19,000 multiplied by the number of hours that it is operating. And then the second mine is $13,300 per hour, and that one is Y hours. So this is our cost equation. That's what we're going to try to minimize. So at the end, what we'll be doing is identifying that feasible operation region, and we will substitute the vertices from that region into this cost function. So we need to create our region by writing out some constraint equations and graphing them. Okay, so when you're looking for constraints, think about what you have totals on. So the thing that we have totals on in this problem, we have production requirement totals. We need 420 tons of regular grade ore and 540 tons of low grade ore per week. And that is a requirement that they have to meet. So we're going to write an equation for each of those. And then we also have a constraint for time, and that is that we know that they can't operate more than 40 and 38 hours respectively. So I'm going to write out those time constraints first because they're the easiest, and then we'll write out the regular grade and low grade requirements. So for time, we know that the first mine can only operate 40 hours or less per week. So X is the first mine's hours. That has to be less than or equal to 40. Now I'm going to go ahead and plot that on my coordinate plane, keeping in mind that I always usually plot things sort of in the middle to start with in case other things become, so that my next points that I plot, I have room for them. And then our second mine is 38 hours per week or less. Okay, so X has to operate at less than 40 and Y has to operate at less than 38 hours. Okay, so now let's do our regular grade OR. For regular grade OR, we need to produce at least 420 tons. So I'm going to set up my equation, and it's got to be greater than or equal to 420. And it tells me about the first mine and the second mine. For the first mine, it's 6 tons of regular. So that's 6, and that's per hour. So we times it by the hours. 6x for the first mine. And for the second mine, it's 18 tons of regular grade per hour. So that will be 18y. We could go ahead and find the intercepts and plot this line now. Again, to find our intercepts, we set each of our variables equal to 0. So if x equals 0, we have the equation 18y equals 420. And again, I'm using equals because I'm just looking for where it's crossing the x-axis. So if we divide by 18, we get 23.3. And don't worry if it is a decimal value. So 23.3, I just know it needs to be less than 38. I wouldn't, worry too much about exactly where it's at. Just make sure you get it relatively correct compared to the other numbers on your axis. So we found our first intercept, and now if y equals 0, we'll get our x-intercept. And if y is 0, we end up with the equation 6x equals 420. So we have x equals 70. And that, of course, will be over here. Connecting those two gives us our constraint. Now, this was that we need more than 420. This is a greater than relationship here. So we would shade above that line. So it looks like so far our region is this trapezoid. But we have one more constraint. Our other constraint is for the low grade ore. So for the low grade ore, they need 540 tons per week, at least. And if we look at how our mine's production goes, it looks like the first mine produces 18 tons of low grade per hour. So that'll be 18x. And then for the second mine, it's 9 tons per hour. So here is our equation. And again, we need to find the intercepts. So if x equals 0, we have the equation 9y equals 540. And again, I'm just subbing in 0 for x and then solving for y. And if we solve that, we get y equals 60. So 0, 60. And now we'll find our x-intercept. If y equals 0, we have the equation 18x equals 540. And so if we divide by 18, sometimes my tablet does not get my handwriting very well. That's that x is 30. So I'll connect those 2 points to get our low grade constraint. And so it has to produce more than that. So I'm going to erase away this, and that will leave us with our feasible region. We have all of our constraints taken care of. And what we want to do is minimize our cost. And so we need to check the cost at each vertex. So linear programming tells us that if we determine that feasible region, the minimum and maximum are going to occur at a vertex of the shape that is formed. So actually this vertex up here, that's the point 40, 38. That one actually represents the maximum cost. If I run each mine the absolute maximum that I can, that's going to give me the maximum cost. Now I'm after a minimum cost. So we have 3 points that we need to test. Maybe we want to run that first mine for 40 hours, but not run the second mine very much. Or maybe we want to run the second mine a ton and not a lot on the first mine, or maybe it's somewhere in between. Now, the tricky thing here is that none of those points are known points. Now, we know part of them, but we just don't know what their exact location is. So I'm going to label them. I'm going to label this one A, this one B, and this one C. Now, point A is not too hard to find because we know that its Y value is 38. So we can just use one of the equations here to figure out the X value. So I'm going to go ahead and use this one. So I have 6 times X plus 18 times Y, and I'm going to sub in 38. And that is equal to 420. And again, I'm doing this equation subbing in 38. So that's an 18 times the 38. Oi. Okay, 18 times 38 is 600. Did I times that right? And we're trying to figure out what X is. So 18 times 38. I think I have an error. Sorry. Oh my goodness. It's probably because of my handwriting. There's something wrong though. Let me go back just a second. Oh my gosh, I see the problem. I'm so sorry. Okay. All right. I'm not taking that out of the video because it's good to think about things and good to see that other people have to think about things. Point A, we definitely know has a Y value of 38. And it is also located on the green line. So for the love of all that is holy, use the green line to sub in because it's on the green line. So I'm sorry, I subbed it into the blue line. So I need to sub it into the green line because that's the line that it's on. See, it's on the green line. So 18x plus 9 times 38 is equal to 540. So 9 times 38 gives me 342. So I have 18x, and then I'm going to subtract that 342 from both sides. I can't believe how illegible this is. My handwriting is not usually this bad, but I don't know, maybe my battery's dying in my pen or something. Okay, so 18x equals 198. Oh my gosh. And we divide by 18 to get 11 as our x value. So that's one of our vertices. So the vertex was the x value is 11 and the y value is 38. Oh my goodness. It's like the 8s are especially bad. 38. So we'll use that vertex in a minute. That's vertex A. Now we also need to find the location of vertex B. Now vertex B is similar because it is at a known x value. We know that the x value is 40, and we know that it's on that blue line, so we can sub that into the blue equation. So 6 times 40 plus 18y equals 420. So we're going to do a little subtraction and dividing. And so we get 18y equals 180. So we divide by 18 to get y equals 10. Wow, 10. Okay, so point B, the x value was 40 and the y value is 10. Okay, and now we have one more point that we need to find the location of C. Our minimum is going to happen at one of these 3 points. So for our last point C, it's where the green line and the blue line cross. So that's where we have to do our whole system. So I'm going to draw a line here. See if I can do my system right below it. So I have 6, let's see, erase. Sorry, I'm going to write that green equation first. 18x plus 9y equals 540. Now I want to eliminate one of my variables so that I can solve for point C. I'm going to times that blue equation by 3, negative 3. And I'm going to write below that second equation. So if I multiply by negative 3, that's negative 18x. 18 times 3 is 54. And again, I'm timesing by negative 3. So negative 54y. And 420 times negative 3 is negative 1260. So if I combine those two equations, I get negative 45y and then 540 minus 1260 is negative 720. So we divide and get 16. Now that I know what y is, again, that's point C. It's on both the green and the blue line, so I could sub it into either of those. So I'll just sub it into the first one. 6x plus 18 times 16 is equal to 420. And so if I solve for x, I get 22. Wow, that's the best looking 22 I've ever written. Okay, so our X value was 22 and our Y value was 16. Need a new battery, I think. Okay, so we're almost done. We have to sub each vertex into our cost function to figure out which vertex gives us the minimum cost. So, like for example, in the first one, 19,000 times 11 plus 13,300 times by 38. And we get a cost of $714,400. And again, we just repeat that, subbing them into our cost equation that I have outlined in red at the top. 19,000 times 40 plus 13,300 multiplied by 10. And we are looking for the minimum here. That's something to definitely pay attention to. Some problems are looking for a max. Oh my gosh. I swear to you, my tablet hates me today. Some of them are looking for a minimum. This one's a minimum. And we've got one more to sub in. Okay. 600, oh my goodness. And 30,800. Okay, so the question is how many hours per week should we operate? So it looks like to minimize the cost, we should operate mine X at 22 hours. And we should operate that second mine at 16 hours per week. Oh my goodness, I know you guys need this video, otherwise I would never post this. The handwriting does not work. Oh, it's very frustrating. Okay, so that's our answer to this example. 22 hours for the first mine and 16 hours for the second mine. Those are not interchangeable, so make sure you get them associated with the correct mine. All right, so that is it for minimizing cost. There is a write-up of this that is organized and has good handwriting on my website or in Canvas on the files. So let me know if you have questions, and best of luck to you on this topic.